Even though we have built our cosmological model based on observations and theories and mathematics supporting those theories, there are a few clues that the universe isn't completely adding up. You might have come across the term crisis in cosmology. Essentially, this crisis emerged when various techniques for determining the universe's age began producing conflicting results, a problem that persists to this day, and cosmologists have no idea why. The James Webb Telescope, with its recent images, has worsened the crisis even more. But for now, here's a very quick refresher. The universe is expanding, and distant galaxies are moving farther away from us. To determine the universe's expansion rate, one approach involves analyzing the cosmic microwave background. This is what we get. Then there's another method relies on understanding the expected brightness of distant supernovas. By comparing this intrinsic brightness to their observed brightness, we can infer the universe's expansion rate at the time those supernovas occurred. When we calculate the expansion rate using this method, also called standard candles, this is what we get. So the expansion rate of the universe is called the Hubble constant. However, the difference between the result of the two methods is called the Hubble tension, and this, my friends, is the crisis in cosmology. But this is not the only crisis anymore. There is a new crisis in town, and it appears to be a distant cousin of the crisis in cosmology, and it is that cousin that we very much despise.
I spent all my life developing a particular theory of the universe, and now that theory is being questioned. I welcome that, because that's how we move forward. That's how we make progress in science.
When we look up in the sky, given you are not in a city or a place obstructing starlight, you see countless stars. You also see the Andromeda galaxy as a smudge amidst the many stars. That's because the universe is filled with stars and galaxies. But the question is, how much of the universe do they fill? In other words, how much matter is actually there? A simple question, the answer to which is anything but simple. This dilemma exists largely because current cosmological observations simply disagree on how matter is distributed in the present-day universe, and this has given rise to the S8 tension, aka the cousin we do not like. Now, the S8 tension is a measure of the lumpiness or clustering of matter in the universe. To put it simply, imagine the universe as a massive puzzle, with its scattered matter forming the individual pieces. Scientists aim to decipher how this matter is arranged and how it clusters together. There are two primary approaches to studying this. The first involves precise calculations based on low redshift observations, such as weak gravitational lensing. This phenomenon occurs when the intense gravitational forces of massive entities like black holes and galaxies bend and distort light from distant objects, acting like cosmic magnifying glasses. This process unveils unique insights into the expansive universe. However, there's a discrepancy. The S8 value determined through the second method, which depends on the standard cosmological model rooted in cosmic microwave background data, does not align with the values obtained from low redshift observations. This discrepancy is central to the enigmatic S8 tension. It highlights a missing piece in our understanding, resisting reconciliation despite countless hypotheses, observations, and the theoretical constructs underpinning them. In an effort to shed light on this mystery, astronomers leveraged one of the most advanced supercomputers in the world to conduct the largest cosmological simulations ever undertaken. The scale of this project becomes evident when recognizing that these simulations required more than 50 million computing hours, utilizing 30,000 processors within the supercomputer housed at Durham University in the UK, dubbed FLAMINGO. The project, with its convoluted acronym denoting Full Hydro Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observations, stands out not only for its immense size and high resolution, but also for its comprehensive approach. Distinct from previous simulations primarily focused on modeling dark matter, FLAMINGO goes beyond gravity alone. Although dark matter accounts for the majority of the universe's mass, ordinary baryonic matter, which makes up only about 1/5 of the total mass, plays a crucial role in shaping the distribution of cosmic matter on smaller scales. Phenomena like galactic winds driven by supermassive black holes and supernova explosions can hinder galaxy formation. Unlike earlier simulations that focused solely on dark matter, FLAMINGO incorporates and monitors ordinary matter, acknowledging that while dark matter governs gravity, the influence of ordinary matter is equally significant. Despite significant achievements, such as successfully modeling the formation of galaxies like the Milky Way and Andromeda, FLAMINGO still struggles to explain the weaker-than-expected clumping of matter in the present-day universe. In essence, it has not succeeded in addressing the S8 tension it was designed to resolve. Alternatively, one might argue that the FLAMINGO simulations reveal a fundamental flaw in our widely accepted standard model of cosmology. The simulation also conflicts with findings from the James Webb Space Telescope and other observatories regarding the distribution of matter in the universe. While the current theory elegantly accounts for the evolution of galaxies, it falls short by predicting that galaxies are 7% more tightly clustered than observations suggest. The updated computer simulation provides far more detail and incorporates the influence of supermassive black holes. However, it's still not entirely accurate, as it remains 5% more clumpy.
The current theory beautifully explains how galaxies evolved, but there's a problem. It predicts that they're 7% more closely clustered together than they actually are. The new computer simulation is much more detailed, and it takes into account the role of supermassive black holes. But that's not right either. It's still 5% more clumpy.
Personally, I think this is a positive development for science because it shows we're making progress, and it's clear that our cosmological model requires significant updates. This is how science advances. Major changes are on the way, and they're already becoming apparent. That's what I feel. What do you think? Drop in your comments below. Also, channel membership is now live. Please help me buy a cup of coffee if you enjoy my content. Until next time.